Alright, what's going on, you guys? Another LeetCode video today. This one's called Combination Sum 2. So we're given a collection of candidate numbers and a target number. They want us to find all unique combinations of candidates that sum up to target. And then the difference between this problem and the original combination sum is that each number in candidates can only be used once. So in the original combination sum, you could take a candidate and then reuse it as many times as you wanted to form or basically to sum to the target. But in this, we can only choose the numbers once. So that's really the key difference there. And the solution set cannot contain duplicate combinations. Yeah, let's get into the whiteboarding for this problem. So we're going to take the second example here. So this is our input array, and then 5 is going to be the target that we're trying to sum to. So basically the first thing we want to do for this problem is just, and you could try to solve this without doing this, but we're basically going to sort this first in ascending order to ensure uniqueness basically in our result vector of combinations, right? We need each combination to be unique. So we basically need a way to systematically go through each candidate, or go through the candidates in order. That way we're only using unique combinations, right? So we're going to sort these first. That's going to take log n time, but it's going to be dominated by our recursive backtracking, right? That's going to have a much greater time complexity. So you don't really need to even worry about this log n sorting operation. But nevertheless, yeah, let's sort these. So we're going to have a 1, there's 3 2s, and then a 5. All right, so now that we have sorted that, let me just erase this. And oops, make that back in full screen. Okay, so yes, this is what we're working with now. Let me actually move this target down a little bit so it's a little less messy. So we've now sorted our candidates, and we're looking for all of the combinations here that sum up to 5, and we can only use each number once. So we're basically going to start our recursion with an empty combination and then this index of 0, because we need to know where to start in our loop at each recursive call. So basically, yeah, let's just start this recursion. So we're going to try and select the first available number here, which is 1. We're going to add it to that combination. We're going to increase our index by 1. So this is what we have now. For our recursive backtracking, we're going to just remove this 1 from the combination and then try to add the next available number, so which is going to be 2. So in this branch, we're going to have a 2, and then a 0 here gets incremented. It was 1 before, so now it's going to be 2. Okay, and then we're going to have a rule also. So we sorted these, right? But what does that do? Well, we're going to be able to check now when we're doing these doing this branching. Okay, like, did we already add, was the previous number the same as the current number? Yes, it was. So we're going to skip. There would actually be two numbers here that we're going to skip, right? So we're going to skip those 2 2s, and then, but we are going to add this 5, right? Because it's different. So we're going to go over here, and we're going to backtrack that 2, add the 5, and then I got to make sure we get this index correct, because we were at 2 here, then we would have been at 3, 4, and then we're going to be at 5 now here. And notice also this 5 sums to the target. So this is going to be pushed to our solution, our combinations, right, for our solution. So yeah, so let's go down to the next level of the recursive tree. So we have a 1 here. We're going to add the next available candidate, which is a 2. We're going to increment that index, and that's the array we end up with, or the combination we end up with. So we would do this again, but we see that this 2 is the same as the previous number. So actually, let's do this way. I do want to indicate that we're skipping some numbers, so we would try to go this way with the 2, but it's the same. We try to go that way with the 2, it's also the same. So neither of those calls would happen, but we get to the 5, and we would try to do that, but we're exceeding our target. So we would skip that call 2, because, you know, if we try to backtrack this 2, and basically this is, I'll show what this would look like. We would have a 1 here, we would try to add the 5, but this sum is greater than our target, so we're not even going to consider this. So that's going to be it for that. And then let's go back to this part of the tree before we start going down. So for this 2, we would add, and let's see. So there is a duplicate number here for the next 2, but there's an exception here. So whenever we're at the first iteration of our loop, we're not going to check for the duplicate case, and that's going to ensure we have all the combinations we need. If we didn't exempt the first iteration from being added, then this wouldn't work out. We wouldn't have all the combinations in our result, right? All of the pos. So to ensure that, we're going to include this 2 because this is the first iteration. So we'll have the 2 here, and then this index is going to be 3. All right, and then let's see. So we're going to try and backtrack this 2, and then basically the 2 we just added was this one. So we'd be trying to add this 2 next, but now this one doesn't get added, right? Because it's not the first iteration. So we would try to add another 2, and it wouldn't go through. We'd also try to add a 5, and that obviously exceeds our target there, so that wouldn't happen either. Okay, and then for this, you know, we're not going to be looping at all, because our this index basically indicates where we start the loop, right? And it's like all the way at the end, so we're not going to be looping at all. This is where the recursion ends here. Also, there's going to be a return statement, right? Like immediately after we are adding a valid combination, because there's no point adding more candidates to it. That would just get bigger than the target, right? So yeah, so let's go this way, continue with this recursive tree. So we're going to be adding the next number. We always add the you know, the first iteration is exempt, right? Even though this 2 is the same. So we have a 1, and we're going to add another 2 here, and that's going to be a valid combination because it sums to 5. So let's indicate that as part of our solution. We would try to add we try to backtrack, add the other 2, but obviously we can't do that because the 2, we just used a 2, right? So, and then we try to backtrack out of 5, but that would be too big. So that call wouldn't go through either. And this would actually return here, right? Because there's a return whenever we have a valid combination. So this is where the this is going to be a leaf node, basically. All right, and then we have to just account for this. So we would try to add another 2, and that would just be too big, right? So and it kind of seems to me like we're like missing a combination or something, but let's check. So nope, the only answers are 1, 2, 2, and 5. So this was done correctly. This would also end because, you know, you would try to add a 2 that would be bigger than the target, so that wouldn't work. And then you try to add a 5, that obviously also wouldn't work. So that's it for the walkthrough of the algorithm. So yeah, so let's go over the time and space complexity, and then we'll get into the code. So the time complexity for this is going to be big O of 2 to the n, way simpler time complexity than the original combination sum. And that's just because if you notice, you know, so like what are we looking for at each node of this recursive tree? Well, we're basically searching through, in the worst case, every single subset of this candidates array, right? These are all just, we're trying to just look at every single subset, right? And how many subsets are there of any set, right? Well, formulaically, the number of subsets of any set, so what, aka the power set, is going to be expressed by 2 to the n, where n is the number of elements in that set. There will be 2 to the n subsets, possible subsets. So that's why our time complexity is big O of 2 to the n, because we have to visit every single node in this recursive tree, right? So an objection you might have is like, okay, well, if it's 2 to the n, how is the branching factor like 3 to the n here? Or in the worst case, if there were no duplicates, the branching factor could be n. Well, as we go down our tree, the branching factor continues to decrease because there's less and less options for candidates we can add, right? So because the branching factor decreases, it's not going to be uniform or consistent throughout the tree. It's easier to just look at this as, you know, how many nodes are there in the tree? Well, we know there's at max 2 to the n, so that's why the time complexity is big O of 2 to the n. And then the n log n for sorting, you could say plus n log n, right? But that gets dominated by the 2 to the n, right? That grows very quickly. So in terms of the space complexity, I'm just going to look at auxiliary space for space complexity analysis. I'm not going to consider the extra space for actually building the solution. So in terms of auxiliary space, we really just have the recursive call stack. And when you're considering a recursive call stack, it's just going to be the height of the tree. So we can see that this tree is going to have at most the number of candidates, right? So we could just say the space complexity is big O of n, right? Because basically you're building subsets as you go down the tree, and at most you're going to have n elements in your subset. So big O of n for the space complexity. Obviously that's going to be limited by the target, and you could do some fancier math to get a better estimate here, but we're just going to go with big O of n. So let's get into the code here. So the first thing we want to do is just sort these candidates, right? So we'll say from candidates.begin, so the first iterator, to candidates.end. We're just gonna go ahead and sort those candidates. We need a vector of vectors, or a vector of integers, right, for our result. I'll just call it res for short. We're gonna need a vector, an empty vector for our first combo for seeding that recursion. And then I'll just overload combination sum 2. For our recursive function, we're gonna do it in a separate function. That way we can have all the parameters we need, and we'll return res. All right, so we're gonna implement this recursive function as a private class method. So it's gonna have a void return value, and we're just gonna overload that combination sum 2 method. So the first thing that we want to pass in here is going to be, first thing that we want to pass in here is going to be, let's see, well, we're definitely going to need the the target, right, that we're looking for, we're gonna need an integer I, right, to know where to start looping. We're gonna need the target, and we'll just use the target to also, we'll subtract candidates we're adding from the target. So in each path, we know, what the sum is without having to do any kind of linear work. So we're gonna need that. We're gonna need the current combo, so that'll be a vector of integers called combo. We also want the result, so vector, that's just a vector of vectors of integers, and these are all by reference, that way we don't have to deep copy them. And then finally, just the vector of those candidates. That's a vector of integers. Okay, so that's a lot of parameters there, but that's everything we need. So let's go ahead and seed the recursion. So we're going to first put in the index there, which will start at 0. Our target, which was given to us as a function parameter. The combination, which is empty at first. Let's see, the result, and then those candidates. Okay, so the first thing we want to do here is just check, okay, is our target equal to 0? When a target's equal to 0, we know we've basically have a combination that sums to the target. So we're just going to push back, let's see, I don't know why I didn't add another bracket there, or curly brace, but we're going to push this current combination to the result, so the combo, or res.pushback combo, and then we want to return. We don't want to add any more candidates, so we're going to return after that. Okay, and then we want to basically do our loop. So we're going to loop, just do a for loop. We're already using i's, but from I to the size of candidates. So we'll say j equals I. Well, j is less than candidates dot size j plus plus. So just using j as our iterator, or our index that we will increment. So we've got to check, right? So we've got to make sure this element's not the same as the last one, and then also we're going to exempt the first iteration like we discussed, right? So we're going to say if j is greater than I, so we're only checking for not the first iteration. So if j is greater than I and candidates j, just to see if this candidate is the same as the last one, so j minus 1. If that's true and we're not at the first iteration, then we're just going to continue. We'll skip over that candidate. Okay, otherwise we want to go ahead and add this candidate to the combination vector. So we'll say combo.push back candidates j. And then we do our recursion, so combination sum 2. We're going to increment the index by 1. We're going to pass in target minus the candidate we just added, so candidates j. We also want that combo, the result, and then the same candidate's input. So then we do backtracking, so we'll do combo dot push, or combo dot pop back, just to remove that last element we added for the next iteration where we're going to try and add the next available candidate. So this is pretty much it for the code. There's one more check, right, that I forgot. So we only want to add a candidate if it's, so if candidates j, and that's really target minus candidates j. So we don't want to exceed our target, right? And using the actual target in value to determine whether or not we've exceeded that by subtracting the candidates from it. And once we get below the target, once we get below 0 for the target, we know we've exceeded it. So if target minus candidates j is less than 0, we want to go ahead and not do this. So let's just say greater than or equal to 0, and we'll put all of this inside of there, just to ensure that we're not exceeding the size of target. So that's pretty much it for the code. So let's go ahead and run this. Candidate, so it looks like we have a typo somewhere. Let's see there. Let me go ahead and skim through this a little bit. Doesn't look like there's anything else. So yeah, hopefully this video helped you understand the problem better. If it did, leave a like and subscribe. I'll see you guys in the next video. Peace.